All right, well, let's go ahead and get started. We do have a lot of topics to cover, because we are slightly behind schedule, okay? But before, I go into the actual topic, let me just kind of share certain things with you. I'm pretty sure some of you or most of you know that certain people have told me that I'm required to closed caption everything that I put online. Have I talked about that in this class? No? Okay. So if you watch my YouTube videos and find it useful, you might want to pay attention, because I was told by certain people on this campus that I have to supply closed captioning of anything that I post on YouTube. Okay, so that means I have 640 minutes of closed captioning to do every week. Not one semester, every week I have 8 80-minute sessions, and this is even before my second 8-week classes kick in. Okay, yep.
Who in the hell told you that?
I would not name those names because I do not think those people are responsible for setting the policy. They're really relaying the message. Okay, so I'm not going to shoot the messenger.
Well, I mean, millions of caption things that you put on YouTube that you put on U.S. television. Otherwise, you're not required.
Well, I think someone, not at the college level, okay, either misinterpreted Section 508, which is the accessibility section, that talks about how government agencies, have to play by certain rules and make sure that the material are accessible to people who have accessibility requirements. I found the actual phrase. It says, it basically says, upon request, alternate format of the content must be provided. But the key word is upon request. It doesn't mean that everything has to be closed captioned to begin with. Okay? In case anyone in this class said, okay, I need closed captioning, I can then decide what to do about it, because I can present the content in a different way. We can have DSPS to send someone over here to do live captioning, real-time live captioning. Okay, there are many ways to do it when I have someone requesting that. But just to blanket everything, when I have 0 students in many of my classes requiring closed captioning, and I still have to do it, which means if I don't do it, I cannot put it online. So 100% of my students will lose access to live recording in my class in order to benefit, or to be fair to what? 0% of my students. That does not compute in my book. Okay, even if it's 1%, I can still understand that sometimes we do not want things to be unfair to people with disabilities. Okay, I take it. I understand that part. But when there are 0 students who have that requirement, then it does not make sense at all. So I just want to rant a little bit, and I'm resisting it right now. Yeah, as the policy messenger, because I'm pretty sure they did not set the policy. As they said, Tech, why are you resisting? Well, because I am resisting. Resisting the resistance is futile.
Resist the empire.
The empire. All right, so now that I get that one out of the way and more people are now in the class, we can talk about the solution of the homework assignment. Okay, so this homework assignment is by design confusing to make sure that you exercise everything that you need to exercise in order to understand those concepts. So what I'll do first is to take a look at the solution. Instead of just giving you the solution, which is really easy, really simple, I'm going to work on this, step by step, and kind of show you how I would approach the problem, and also to explain those concepts again, because I think those concepts are very important in this class. The pace of this class will pick up, okay, because we are falling a little bit behind. I wouldn't say very much behind, but we are behind a little bit at this point. All right, so I'm getting the file and using a terminal to work on it. All right. So I'll do a tar xlvf /temp/ what was it again? Find it to. Go. Change to that folder, and we'll take a look at the folder first. I can use mousepad to look at it. I think the font size is better in mousepad. All right, so there we have it. So here's your homework assignment. No, that's not the one. This is the wrong one, but it's not a bad one to try either, okay? How many people have tried out this one? Nobody.
Where is that?
Is it hidden from your view? It may be hidden. I think it's just hidden from your view. I'm gonna unhide it, and use it also as yeah, it is hidden right now. Yeah. I clicked on the wrong one. Sorry about that. There we go. That's the one that we. Yeah.
Don't you need version 2?
Hmm?
You need the other one? You just saved a copy of that one.
Do we have version 2?
Was it?
No, this is the one that we have. That's ours. Yep. Okay, so let's try that again. And by the way, this is how you remove a folder, and its content in Linux. RM by itself, will not destroy a folder unless the folder is already empty, and you have to specify, -R in order to do it recursively. So if you want to remove a folder and its content, you use -R and then lowercase f in order to remove, a folder and all of its content. This will do it recursively. So it can potentially be kind of dangerous if you apply it to something that you do not intend to delete. All right, so we'll go ahead and do this part, go to the folder again, and see if this is the one that we want. Yep, that's the one that we want. All right. Okay. So the other one is actually more difficult because it has 3 unknowns, instead of 2. This one only has 2 unknowns. We can talk about the other one because I think it's really good exercise to also work with the other one. All right, so let's take a look at this one first, and I will kind of show you how I would approach this problem. Many people would say, but Tag, you created this homework assignment. Surely you already know the answer, and so it doesn't really count. Well, because my memory is not really that good, sometimes I would write an assignment and I would forget about the solution if I don't keep track of it, and I did not keep track of the solution of this one either. So to me, it is just like a brand new homework assignment. It's as new to me as it was to you. Okay? Some people do not believe it, but people who have taken several classes from me definitely know that is true. Right? How many times have I taken role in this class? Well, there you have it.
How many times have you taken role collectively in all the classes you've ever taught?
Well, there you go. Yep, exactly. Without being prompted by my students either, right? All right, so what we want is for ECX as a register to have that particular value by the time we get to the test year label. So that means the 2 instructions that will be executed immediately before this will be the ones that are important because those are the ones that actually put something in the ECX. None of the other instructions will do anything about ECX because you don't see ECX or any parts of ECX as the second operand of any instruction except for those 2. Okay. Let me turn on the line numbers so this way we can refer to the line number as well. So there you go, we have line numbers. All right. So the first thing I would do is to look at this hexadecimal number here and break it into bytes. Okay, because you have to look at it in bytes in order to figure out, okay, what am I searching for in memory? What am I going to copy into ECX to get this done? Are we making any sense so far? Now, how do I know that I'm going to copy something from memory instead of, I just need to specify this content or this particular value as an immediate operand and I'll be done? What is the restriction here? The restriction has to do with the operand of this instruction. This operand here is already done for you. You cannot change it. And is this a immediate operand or is it a memory type operand? Is a memory type operand? Yep. Go ahead. No, no, you cannot just take a dollar sign in front of it and turn it into a immediate operand. Yep. Okay, so we have a memory operand as the first operand, so we know that we are copying from somewhere in memory into ECX in order to end up with the pattern that we want, which is this part here. So the first thing I need to do, I'm going to do it here in place in this file. So what we want to do is, we want to look at these bytes in sequence. Okay, so we'll try to list these bytes in sequence. The first byte is a 0. The next byte is 0, 1. And then the next one after that is also a 0, 1. And then the last one is a 1, 0. Okay, the way I can do this is because I know the Intel architecture is a little endian processor. The least significant byte is the one at the lowest address. So that's why the 0, 0 ends up being the first byte because it is the least significant byte. The next one is 0, 1, and then 0, 1, and then 1, 0. But by looking at the instruction on line 13 and also the next instruction, I know that this byte is not important, at least for the time being. Because this is the second least significant byte, and it is overrated by line 14. So I know when I'm only thinking about line 13, this one is not important yet. Okay, I have another chance to change this byte to the intended content. I only have to worry about mostly the other 3 bytes.
Isn't it the one to the right?
No, this is the one because 0, 0 is the least significant byte. That's the one that is loaded into register quote unquote CL, which is the low byte. This is the one, the highlighted one is the one that is going into CH, which is the second least significant byte, or bit 7 to bit 15 in ECX. I'm reading this, backwards because I'm taking little endian into consideration. Right. All right, no problem. Okay, so now that I know what sequence I'm looking for, which is basically starting with 0, 0, whatever is here does not matter. 0, 1, and then 1, 0. The next thing I want to do is to look at the actual memory content that I'm initializing and find where that pattern is. So one thing I will do is I'm going to list all the bytes in memory using a particular, using just a byte sequence format. Instead of using .in, .byte, .word, I'm translating everything into .bytes. Because that way I can make a match between what I need versus what I have. Are we making progress here? Okay. So now I'm going to look at line 3, which is a integer. A .int means 32-bit. So that means if I use, now from here on, I'm not going to use 0x as a prefix because everything that I'm doing here is going to be in hexadecimal. So I'm not going to use 0x as a prefix for base 16. I'm just assuming everything is base 16 just so that I don't have to type as much. Okay. 0, 1 is the least significant byte, which is this part here. 1, 1 is the second least significant byte. Oh, but that's only taking up 2 bytes. What about the other 2 bytes?
0, 0, 0, 0.
They're all leading zeros, so that means I have 0, 0, and 0, 0 as the other 2 bytes. Okay? Because .int says, I need to allocate 32 bits in order to represent the value that is next to .int. So how do you use 32-bit to represent something that does not need 32-bit? Fill up all the implicit leading zeros, so that it has that many bytes. Are we still doing okay so far? Okay. So the next thing we have to do is the dot byte. The dot bytes are easy because they are really just as specified. The order is just as specified. And then we have the dot words. Now the dot words have the same trick because the first dot word is only 1, 0, but we are specifying that we want to represent hexadecimal 1, 0 with 2 bytes. So that means the least significant byte is a 1, 0, but the most significant byte is just 0, 0 itself. So we have 1, 0, and then 0, 0 here. And then the next one is a little bit tricky because it's 0, 1, and 0, 1. The least significant byte is 0, 1, and so is the most significant byte. Because there's an implicit 0 in front of the 101 in the second dot word. And then we have line 6, right? We have line 6, which is L2.int L2. The address, I can never really predict where it's going to be. So what I would do is I'm just going to use 4 unknown bytes to represent the space taken up by that particular .int. I do not know exactly the value and I should not have to know that exact value either. Are we still doing okay? And then we have the L3 label on line 7 that only gives me 2 bytes, and since they're dot bytes, they're pretty easy to deal with because it's just really the way they are listed is the order that they will be in memory. Are we doing okay so far with this map here? And just to make it easier for me to find out the address of something, I'm going to put label L1 here because it really is the first byte of the dot int, and then L2 is all the way over here because it is the address of the least significant byte of the dot int on line 7, and then we have L3 all the way over here. So this is helpful as well because now I'm defining 3 bookmarks, so to speak, so that I can refer to certain byte locations using just the label name. Now, using these labels, I can now say L1 plus 1 is the address of the 1, 1 next to the 0, 1, and so on. Are there any questions about this particular step, which is just adding labels to the memory map that I have done in the first step? Go ahead.
For the 0, 0, 0, 0, on like the fourth one.
The third and the fourth?
Yeah, third and fourth one. Where is the actual set of zeros coming from exactly? Like, is it from like 0x?
It's from the dot int.
The dot int.
Yeah, the dot int says, I need to represent 1101 in hexadecimal using 32 bits, right? So how do you represent 1101 in hexadecimal using 32 bits?
So exactly extra sheets.
Yeah, because you have to fill it up to 32. If you take this to the extreme, if that dot int is not 1101 and instead it's just 0, how many bits do I need to represent 0? The minimum number of bits that I need to represent 0 is 0. Is 1, okay? I need 1 bit to represent 0. So what about the other 31 bits in that case? They're all zeros. So you have to kind of fill it up, until you have the right size that the directive is asking for. Okay. Right. Are there any questions at this point? Go ahead.
Oh.
Go ahead.
For later on, since we're using include L, does it matter that you specified L2 as dot int? I mean, can you specify as something else as like a dot word or dot byte?
It does not matter. When you are using the move out instruction, the boundary between the dot in, dot word, and the dot bytes disappear. There are no actual boundaries between those allocations.
Okay. So really, you just said for L2 is a dot byte L2, and it just makes up the one.
If I use L1 dot byte,
No, wait, L2.
L2,
This is dot byte L2 to allocate.
that would not work because L2 is an address, and every address in a 32-bit mode program is 32-bit itself. So if I try to represent 32 bits or something that requires 32 bits and only give it 8 bits, the linker would actually complain and say, no, cannot do it. Because the number does not fit in the number of bytes that I'm allocating. Go ahead.
I would just ask a little off topic. If you were to try and allocate too many, like if you were to have dot bit 0x101, would it not work? Would it give you an error? Would it work? Or would it work and then you'd have garbage?
If you okay, so you're saying that what if you have a dot byte and instead of something that fits within a byte, you give it like 101 in hexadecimal. Either the assembler or the linker will complain, because it really is the same thing as what we said. A dot byte L2, would not work. Right. Those are all very good questions. And then the other thing is, you can always test it. Because you can just write a program and do exactly what you said and see what kind of error message comes out of it. That would be a good experiment to run because in the future, if you see messages like that, then you know exactly why the assembler or the linker is complaining. Then that will help you with your homework assignments in the future. So if there are are there any additional questions about what I have done up to this point, which is just mapping out all the bytes? Now, once all the bytes are mapped out, then I can try to look for the pattern that I'm looking for. Okay. So the pattern that I'm looking for is already displayed here. I'm going to pull this down just a little bit if people in the back cannot see it, you have to let me know, so I can kind of adjust everything so that you can see everything again. In fact, what I can do is I can just copy and paste this portion all the way to the top, so this way I can align this here and try to look for that pattern. So I'm going to remove the 0x so everything lines up, except these two I don't really care at this point because the next instruction is going to override this particular byte anyway. So I'm just looking for 0, 0, whatever, 0, 1, and then 1, 0. Okay, so I'm going to map it here. Hey, that's a match, right? Are we doing okay so far? I have just found a match for what I'm looking for. It turns out to be L1 plus 2. Okay, L1 plus 2. Now, L1 plus 2 has many names. Okay, so I'm just going to use another line of comment here and say this is known as L1 plus 2. But it also has other aliases, right? Because I can start with L2 and use a subtraction to figure out, okay, exactly what is it. I'm not really good at looking at the displacements and figure out the actual displacement. So in this case, I'm going to do exactly what a kindergarten student will do. I'm just going to count. L1, L2 minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, and minus 8. Okay. Is that okay? Okay, did I miscount? Because sometimes you'll do stupid things like miscounting numbers. Okay, so I'm assuming it's L2 minus 8. If I do make a mistake later on, I can probably spot it and fix it too. Go ahead. Oh, okay. All right, so this is L2. This is also known as L2 minus 8. Great. So what we have here is we know that the effective address of this operand has to be L1 plus 2 or L2 minus 8, which is referring to exactly the same location. Are we doing okay so far with that? Okay. So what I'm going to do here is to use that equation and then just say that that the result of that equation has to be L1 plus 2 or L2 minus 8. They are basically the same number. The equation goes like this. Okay. The displacement is 4. The base register, I'll just say it is the content of EAX at that time. And then the rest is the product of EBX and the scale. So we have EBX, the content or the value of EBX at the time, times 2. So I want this to be the same as L1 plus 2, or if you want to express it as L2 minus 8, that is good as well. Are we doing okay so far? So I'm putting a constraint here to say, okay, I know what the outcome is supposed to be. I don't quite know how to get there, but I know what the outcome is supposed to be. Is that okay?
How are you knowing that the minus 4 EAX is?
Because that's our general equation that we talked about last Thursday, which is D plus I times S,
Oh, yeah.
which is the most general form of a memory operand for the I386 architecture. Okay. So that is useful because now I know, okay, so how can I get that sum to be like that? Okay. Now, if you want to, we can try to work out the byte also and think about the alternatives of that byte because that one actually has alternatives. Okay. Now, when you look at this number here, okay, -4 is just a fairly small displacement number. EBX times 2, well, can be a large number depending on the value of EBX. But instead of doing this, okay, instead of trying to solve my problem right away, I'm going to try to make the other equation. The other equation refers to this mystery here. Okay, this one does not give me as much room to play with because CH needs to be a 0, 1. Now, if I want to move a 0, 1 into CH, I can pick this 0, 1, I can pick this 0, 1, I can pick one of these two, and those are the 4 choices that I have. Okay, so that means the restriction now is I can choose between L1, I can choose L1 plus, let's see, plus 1, 2, 3, 4, plus 4. I can choose this one here, which is L2 minus 2, and also L2 minus 1. all of those locations correspond to a byte location that has 0, 1 in hexadecimal as its content. Am I still doing okay so far? I got 4 choices for the second instruction. The equation of the second effective address, or EA, is a little bit more restrictive because it only has 1 register. So when I look at the second instruction, it is something like this. So the effective address is L3 minus 4 plus the content of EBX. Okay, so this has to be the same as L3 minus 4, I think, plus the content of EBX at the time, and you can choose between one of these. So these 2 lines, line 8 and 9 as comments, is now giving me all the constraints that I need to satisfy in order to make this work. Am I doing okay so far? And I know this is not a math class, but I think at this point, you guys really should have enough math background to solve something like that. Okay. There's actually a big clue too. There's a big clue because L2 is .int .L2. That one should come as a kind of clue because what is it doing here? Why do we have something that is interesting like that? Okay. All right. So let's take a look at this one here and see whether we can solve this problem. Okay. What do you think? We have 2 equations, 2 unknowns to solve, but one has 4 possible alternatives. The other one only has 1 single alternative. Do you think we have enough constraints to find the actual solution? Yep, we do. Okay. So how do we go about doing that? Well, you can try all the different combinations, right? Because there are really only 4 things you can try. The 4 things you can try is to say, okay, I want this expression to be just L1. Then you can figure out what EBX has to be. Once you figure out what EBX has to be, you plug it into here, and then you say, if EBX is that value, what would be the value in EAX? Can I get EAX to that value? Nope, there's no way to do it. Move on to the next one, right? Keep going. Okay, so let's go ahead and try that approach and see if it works. Okay. Okay, so we'll say this is option 1, option A, 1. Okay, option 1 is L3 minus 4 plus EBX is L1. Okay. That implies EBX has a value of what? Well, let's go ahead and solve the equation, right? That's, EBX will become L1 minus L3, and then the whole thing plus 4. It's algebra, right? We just move, we add this much to both sides, and we end up with this here. Oh, we subtract that much from both sides. So one side has EBX remaining, and the other side has L1 minus L3 plus 4. Okay, what is L1 minus L3 plus 4? Since we don't even know what the labels are, how can we do arithmetics on the labels?
Set L3 equals to L1 plus
That's a certain number, right?
14.
Is it 14? Okay, so we have, L1, this is L1 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Very good. So L3 is really the same thing as L1 plus 14. So can we solve that equation?
Negative 10? Negative 10?
Negative 10. Okay, so that's fine.
Not really.
Is it? Okay, L1 cancels out L1.
No, that's right.
Yeah, that's right. Negative 10 is correct. All right, so this one works out to have EBX equals to negative 10. So if I plug in EBX being negative 10 into the first equation, what do I get? So we have negative 4 plus EAX plus negative 10 times 2 equals to, if you want to, we can express everything as L1 plus something. Okay. Okay, so how does this work out? EAX becomes L1 plus 2 plus 4, and then we have plus 20, right? because I have to add 4 to cancel out this minus 4. I have to add 20 to cancel out this negative 20 here. So, sorry?
That's not gonna work.
Well, we want to figure out what it is first. Okay, it's L1 plus 26. All right. So can we get L1 plus 26 into EAX? Oh, hold on a second here. What is the one single instruction that you can use to put something into EAX? The very first instruction. All right. So that means you have to somehow get this value into EAX using this instruction, line 25 at this time, because I keep shifting the line numbers, so that's why it is 25 at this time. Is there a way to do it?
No.
Nope. But do we have something that comes close to putting something like that into a register? Now you can play out all 4 scenarios first, okay, and find out which one is possible, or you can take a look at this and go, I get it. EAX has to be something that has close to the address that we want. Okay, not quite there, but has to be an address. Okay, and the instruction on line 25, the first operand is a direct operand. Okay, we are copying something from memory into EAX, and EAX has to end up to be close to a label plus something. Okay.
How about L2?
L2, yeah, L2 is the answer. Okay, if you're getting the sense that okay, we need something that is like that, let's try L2. Then you have found the solution. Okay? Now, if you do not have that suspicion, it's okay. We just play out all the scenarios and see which one will actually solve the problem. So option 1 does not work out. Okay, it doesn't work out. So we'll. And by the way, what is L2? L2 is L1 plus 10. Okay, so we'll make a note of that too. Okay, so we know that L2 is L1 plus 10 because this is L1 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's really helpful if I use a spreadsheet to do this, but since I'm not using a spreadsheet to do it, I have to do all the counting. Okay. All right, so let's try the next one. The next one is, let's say, option 2. Option 2 basically says, let's try something else. L3 minus 4 plus EBX is going to be the next location that might have the content that we want.
L2
and the next
2.
one is L1 plus 4.
Let's try L2 minus 2.
Let's try L2
Minus 2.
minus 2.
Minus 2.
Okay, so let's say that we, for whatever reason, we choose the L2 minus 2 to be our option. So we want to see whether that works out or not. Okay, and we're going to solve the equation exactly the same way as the other one, because we can move, we can use algebra operation and say this is L2 minus 2 minus L3 plus 4. Okay. And in this case, EBX turns out to be L2 minus 2 minus L3 is L2 plus 2, so this is just L2 plus 4, and then the whole thing plus 4, and then we'll go do some canceling and simplification. This L2 is canceled by this L2 here, so we have negative 4, negative 2 minus 4 plus 4, so EBX ends up to be negative 2. Okay. So are there any questions about line 20, or the comment on line 20 that compute that EBX should be negative 2, assuming that we want to pick the 0, 1 as L2 minus 2. Okay. So now we plug that back in to the other equation. So now we have negative 4 plus EAX plus, in this case, negative 2 times 2, because EBX has that value already. And we want that to be the same as L1 plus 2, but L1 plus 2 can also be expressed as L2 minus 8, right? Okay, we want it to be using L2 because one equation is already using L2, so it really helps to use L2 in the other one, so we can do canceling easier that way. Okay, put a comment here, so eventually I can assemble this program and actually run it. All right. So now we solve this equation, EAX becomes L2 minus 8 plus 4, and then another plus 4. The first plus 4 to cancel out this minus 4, the second plus 4 to cancel out this negative minus 4. Are we doing okay so far? Hey, that cancels out, right? Negative 8 plus 4 is 0. So this whole thing just solves to L2. Okay. So now the question is, where am I going to get the L2 from memory? At L2, yes. Great. So I think I have the answer, right? But do you guys see the process? How I apply the reasoning, really kind of step by step. Okay. So now we can just plug it in because now I think I have it all solved. L2 is what we need to be in EAX, and that particular value is also at the location L2. So L2 can go here. EBX needs to be -2, so it goes here. Okay. I'm fairly sure this is the answer, just because the math works out. Okay. So when we test the program, we can put a breakpoint at test here and double check that the register ECX has the value that it needs. Are there any questions about this approach?
Is L2 just because you got L2? Is that split out like L1?
No, because L2 is specifying a memory location. At that memory location, the 4 bytes at that memory location also specifies the value of L2. If you want to see this in the C way, which is not something that I recommend in this class, because the entire purpose of these homework assignments is to make you guys think in assembly language terms and not in high-level programming terms anymore. But since you have taken cisp310 prior to this class, sometimes it might be helpful to translate these concepts into concepts that you already understand. So I'm going to write this one down here. L2.int L2 is kind of like the following. It's kind of like having an initialized pointer. We talked about this in the lab already, so people who went to the lab actually saw this already. So we have a pointer to a void, which means it has no type basically, being initialized to its own address. Okay? And I think C can make this work because you can automatically cast any type of pointer to a void pointer. Because technically the address of PTR is a pointer to a void and not exactly a void pointer. But anything can cast to a void pointer without any explicit casting. But if you want to be sure and make sure the compiler does not nag, you can always just say, oh, let's cast it to a void pointer. That works too. So basically L2.int L2 is kind of doing the same thing here. It's a pointer that points to itself. Is that okay? Is that working out better? Okay. Yep.
What is the line of code in line 35?
On line 35 at this point?
I mean in words. Or like...
Okay, now here's another thing that I can express this in C code, but it may be helpful. It may make it even more confusing, depending on how attached you are to C and C++. Okay, so you have to kind of try not to think in C and C++ terms anymore, except in this case, I'm going to use it to illustrate that concept. So on line 35, I'm going to rewrite, but instead of using it writing on the whiteboard, I'm going to do it in the text file itself. Okay, so line 35 is kind of doing this. Okay, I emphasize the fact that it is kind of doing that. Okay, it's kind of doing something like this. ECX, which is the destination operand, is getting something like this. -4 plus the value of EAX at the time plus 2 times the value of EBX. Okay, if I want to do this in C syntax as closely as possible, this is the way I would specify it. Because the expression -4 plus EAX plus 2 times EBX is calculating the effective address.
It's address. It's not a number. It's the address.
It's just a number. But
No,
what
it
sorry.
represents the address. Represents the address, that number.
Others?
Yeah, in the memory.
The number is
Address in the memory, no?
is an address.
Yeah.
Well, by itself, the number may or may not be an address, right?
In this
expression.
in this case, is address.
Exactly. So in this case, this number is really just a number. I mean, you can plug, EAX and anything into EAX, anything into EBX, and this will give you a number, right? Just an integer value. Yep, go ahead.
Since we previously declared EAX is kind of a pointer, would you want the pointer syntax by EAX?
No, EAX by itself is really just a 32-bit number. It is not a pointer. It has no type.
But I mean, because you want like you have the content and you have the address in C, I mean, you have the address and you have the content.
Right, but that's why this is kind of like pseudo C.
Right.
It's kind of like C, but not C.
Well, even in C, you're just saying L2 is a pointer, and you're saying EAX hold the number that L2 is pointing to. So even in C terms, EAX is just holding a number.
Right, EAX is nothing more than a 32-bit number. It's not even signed or unsigned. It really is just 32 bits. Okay, and same with EBX. So with this calculation, multiplying by 2 is not sign sensitive, so it doesn't really matter whether EBX is a signed number or not. It's still going to be the same calculation. So in this case, I'm just performing a calculation saying I want to add -4 to the value of EAX, and then on top of that, I also want to add twice the value of EBX to the entire thing. So that gives me just a number, a 32-bit number, right? The question now is, what do I want to use what do I want to do with that 32-bit number? So this syntax says, I want to first cast it into an integer pointer, and well, okay, this is not really the best way to do it. The best way to do it is to use int32, because now I'm forcing it to be a 32-bit integer, right? Just to be very explicit. Now it's a 32-bit integer pointer. So I'm going to go to that location specified by the expression and say, okay, give me 4 bytes, give me 32 bits. What are you going to do with those 32 bits? I'm going to copy that to ECX. That is what line 35, if I want to express it in concepts that you already understand in C, would be the concept explained on line 36. Is that okay? Does it make it more confusing, or does it make it slightly better? Slightly better. As long as it's incremental, it's good. We're not going backwards, it's good. All right? Question?
I want to ask that. I don't know if I can understand a little bit of the EAX equal L2 why is it L2? I still don't get it.
Well, let's go ahead and replace all the instructions with the quote-unquote pseudo C equivalents. Okay, because I think that might be educational. This is the first time I do this in this class, using pseudo C to represent the operation in assembly language. Okay, so this becomes EAX, and you might think it is just L2. No, that's not the one. That's not the case. It really is like this. Because L2 is a number. L2 is a label. A label is nothing more than a symbolic name with a number associated with it. You can equate L2 to something more like a pound-defined type of macro. Okay? In other words, L2, you cannot take the address of L2 because it is not an address. It really is just an integer. Okay? So that's what line 33 is really doing that. In other words, we are going to somewhere in memory in order to grab those 4 bytes to put it into EAX. Well, if that is the case, then what will make this other line do? I mean, what is an actual immediate operand doing? Well, the immediate operand is actually simple. Whatever you specify to the right-hand side of the $ is whatever you're copying to the destination, just like that. Are we kind of doing okay here? Because I think this really helps to illustrate the difference between an immediate operand, which does not go to memory to get anything, from a direct operand, which goes to memory to grab something. And once we are done with these three, the last one is actually a simpler version of the one before that, because in this case we have ch, which is a char, and so we have to cast the pointer to make sure it is just a char, or you can say int 8 if you want to. Okay, 8-bit integer. And the way we calculate the effective address is whatever the displacement is plus the content of the register EBX at that time, and that becomes my effective address. So I'm copying one single byte from the address L3 minus 4 plus EBX to CH as a register. Is that okay? Now I can actually translate this entire thing on line 40 to using bit shift operation, bit masking operation, and whatnot, and express the whole thing as an operation to ECX as a whole. But I think that might be more confusing than it's worth.
Just wasn't confusing enough.
Well, it is, it's showing you the effect, but the question is, how do we get to a particular byte in a 32 thing in C? So I'm not going to do that.
I feel like I'm looking at a John Madden football.
Do they talk about this type of thing in your C++ class? How to use pointer casting and do calculations and stuff like that. A little bit.
In 360.
In 360. 360.
In
Yeah.
Rogers class we did.
Okay. That is why it is a prerequisite. Just imagine someone coming from a background of just Java into this class. Okay? In Java, there are no pointers. There's no dereference. There's no pointer casting. So for someone who only understands Java, this is all foreign. This is all new. Because Java has no pointers. Yep. Go ahead.
Line 39. Can you write like move B L3 to CH?
CX.
Yeah.
Yep. Well, no. Well, not always. Okay, I should say not always, because it depends on the least significant byte.
No, I mean the meaning of it's different meaning.
Different meaning.
Yeah. Can you write like move
Okay.
B
Okay. Move
B
B
L3 comma percent CH.
CH.
Mm-hmm. So you move the content of L3, yeah?
But that won't do it because EBX is -2.
No, I mean when you have something in parentheses, it's different meaning of L3.
This is just the syntax. In parentheses we specify the base register.
I meant something else.
Okay.
In this case, it's like the content of L3.
No.
No?
Well, no, not entirely. In this case, it is CH gets int 8 pointer L3.
Mm-hmm.
Okay, so it's not the same. Sorry?
Wait, you go the other way though? Isn't it L3 minus 6?
No, line 41 and line 42 is a pair. So if I have an instruction like line 41, then the quote-unquote C equivalent is going to be line 42. So that's a pair, yeah. All right. So that was your homework assignment, and are those concepts okay now? I mean, is it all right? Yep.
I wish we were hinted at the algebra was to use algebra. I had no idea.
Well, the algebra part is really just to formalize the thinking process. The non-formal thinking process is to say one of the registers has to be an anchor. It has to be close to L1 or L2 or L3. And how do you get something like that into EAX? Well, of all the memory locations that are initialized, L2 or the content at L2 is the only thing that comes close to being an anchor. So that's the informal type of thinking, and then from that you can try to work out EVX, and it turns out that EVX only has -2, and it works out in both cases. All right. So are we okay with the homework assignment? Shall we move on? Okay. So we're going to move on to even more exciting stuff like your flags and also conditional branch instructions. And because I'm not quite done with the discussion yet, so there are no homework assignments today, which only means that I'm stockpiling those concepts. So the next homework assignment is going to exercise a lot of stuff. So it's not necessarily a good thing. All right, so we'll go ahead and take a look at these two slides. The first one talks about subtracting assembly language. And then the next one talks about jump instructions. Okay, so we'll take a look at these two topics. And it'll open up new tabs, new windows, which I don't really like. All right. So we have talked about the multiple flags already. Last time on Tuesday, I gave you an example of using the Z flag so that I can terminate a loop when, I implemented a conditional statement. Right? It's a conditional statement. When two numbers are the same, we will do one thing. When the two numbers are not the same, we'll do something else. Remember that? Okay. So what we'll do today is we're going to take a look at comparison, but for the purposes of seeing which number is larger. Okay? Comparing for equality or inequality is pretty simple. Okay? But comparing for ordering is a little bit harder. So what we want to do is to use a few examples to illustrate, a few cases, and then we'll take a look at those cases and go like, how do we compare numbers? So what we'll do is we'll fall back onto 4-bit patterns because they're just a whole lot easier and quicker to deal with, and we'll take a look at, can we figure out which number is larger using a particular flag for certain values? So first of all, we'll take a look at 9 versus 1. Okay. To compare 9 to 1, you can use subtraction because you're comparing and see which one is larger. The result of the comparison, or the flags that are set after a comparison, can be used to indicate which number is larger. Okay? So we'll compare 9 to 1 and see which one is larger, or we'll try to figure out what kind of bit pattern we'll get out of this. 9 is 1001 in binary. 1 is really just 0001. So when we perform the calculation, this one has 8, and this one ends up with 1000 with no borrow. So I'm going to use this extra 0 here to indicate there's no borrow. Are we doing okay so far with this subtraction? Is that okay? And by the way, am I using the signed interpretation of 1001, or am I using the unsigned interpretation of 1001 here? The unsigned, right? Because the signed interpretation of 1001 as a 4-bit number is going to be negative. Okay. It's going to be negative 6. Oh. It's negative 6 because if you flip it upside down, it's negative 7. Yeah, negative 7. Because you have to add a number to 9, and it has to be 16 in this case. So it's representing negative 7. All right. Okay, that doesn't seem to be too hard. Let's try to figure out all the other flags too. In this case, the Z flag is a 0, right? Okay, are there any questions? Okay, go ahead. Okay.
9 is negative 7, right?
9 has the same representation as negative 7 as a 4-bit number. That's only as a 4-bit number. Okay, if as an 8-bit number, they are not the same.
Okay. But then when you do the subtraction, when you do the subtraction both, it comes out to be 8. 8 is it's not 9. 8 is something different, right? 8 is supposed to be 6.
negative 8 then? The answer should be negative 8 in the unsigned then.
Well, 1000 also has two interpretations. In the signed interpretation, it is negative 8. In the unsigned interpretation, it is just 8. Okay? But the way we do this subtraction is the same. The rules of binary subtraction does not care whether it is signed or unsigned. Yep. I thought you had a question. I was talking about. I thought you were here.
Well,
It's difficult for me to designate a particular person, right? And I don't feel like using a pointer or any ID here. Just walk over and say, you have the question.
Just throw a razor.
I don't have anything that's soft tipped. Okay, the zero flag, the Z flag is 0 in this case. The sign flag is a, come on, give me something here. The sign flag is a 1. The sign flag is a 1 because it's a 4-bit number. The most significant bit is a 1, so the sign flag is a 1. The sign flag is the most significant bit. Is that okay? All right. And we have one more flag to deal with. The C flag we already know is a 0. And we have the overflow flag left here. I am subtracting a non-negative value from a negative value, ending up with a negative value. Is that okay? Yes. Yeah, perfectly okay. Okay, so if it is okay, it's not an overflow situation, so the overflow flag is also going to be a 0. Okay, that's fine. Let's compare the other way around. In other words, we're doing 1 minus 9 in this case, and see which one is larger. So this one is 0, 0, 0, 1, and then we have 1, 0, 0, 1. Perform the actual subtraction here, and we end up with 1, 0, 0, 0. Also, but this time we have a borrow of 1. On this side, I'm not going to say anything because it's not going to. It's a negative value, and a unsigned number cannot represent it. Okay, but we do want to find out what the flags are. The Z flag is a 0, the sign flag is a 1, the carry flag is a 1, and the overflow flag is a 1. I'm subtracting a negative number from a non-negative number, ending up with a negative number. So the overflow flag is a 1 because the sign of the result does not make sense. Okay, but wait, hold on a second here, Jack. Didn't you just say that we're using the unsigned interpretation? So if it is an unsigned interpretation, why do we even want to deal with the overflow flag? Well, we're going to deal with the overflow flag because I'm going to use this example again, but next time I'm going to use it for signed comparison. Okay, so right now I'm trying to use it for unsigned comparison, but I'll use the same bit patterns later on for another purpose. Okay. In the first case, we know that 9 is greater than or equal to, 9 is greater than 1. In the second case, we know that 1 is less than 9, right? So, well, which flag do you think is useful to distinguish which number is larger? Several possibilities. There are several possibilities. We can see that the carry flag can be useful in this case. The overflow flag may be useful in this case. Okay. So what I'll do next is I'll give you another example to see, to try to differentiate and say, okay, can we have more examples so that we can say, oh, these flags do not seem to be useful anymore. Maybe it is just this flag that is useful. So the next case is going to be comparing 1 with 2. Okay. So we have 2 and 1 here, 2 minus 1. And the binary bit pattern is just 0, 0, 0, 1, 0 for 2, 0, 0, 0, 1 for 1. And we do the subtraction. And most of you can probably just do this by hand here. That's just 0, 0, 0, 1. Okay, with no borrow. The Z flag is a 0. The sign flag is a 0. The carry flag is a 0. And the overflow flag is also a 0. Okay. and the relationship is 2 is greater than 1. All right, so let's go, we flip it, okay? So this time we have 1 minus 2. 1 is represented as 0, 0, 0, 1, minus 2. 2 is represented as 0, 0, 1, 0. And we want to take a look at the result here. There is a borrow in this case, right? And the result is, okay, I'm going to do that's going to be a 1. This is going to be a 1 with a borrow, a 1 with a borrow, a 1 with a borrow. So the result is 1, 1, 1, 1 with a borrow. The Z flag is a 0. The sign flag is a 1. The carry flag is a 1. The overflow flag is a 0. And it is the result of 1 being less than 2. 1 being the number being subtracted, and 2 being the number that is subtracted from the first number. Okay, so from these 4 examples, can we single out a single flag that can be useful to indicate the ordering of numbers when they're interpreted signed? The carry, which is also known as the borrow.
For the 1 minus 2 one, shouldn't the overflow be 1 because it's changing signs?
It's changing signs, but it still makes sense because I'm subtracting a non-negative number from another non-negative number, ending up with a negative number. That can happen. Yeah. The overflow flag is set only when the combination cannot happen. Then we know that we're running out of the range of numbers to represent. All right, so that's all good. Okay, so everything seems to indicate that carry flag can be used to tell ordering for unsigned numbers. Yay, cool. All right, so now we move on and talk about signed numbers. And as I said a little bit earlier, I'm just being very lazy here because now I would just add the unsigned interpretation of this bit pattern here. This is -7, right? And this is 1, and we have this sequence here. Now, with this sequence, -7 is actually less than 1. Are we doing okay so far? Okay, let's stop here and say there's 2 things I need to clarify, or 2 things that I need to validate first. The first one is, how do we know 1, 0, 0, 1 is representing -7 using 2's complement and using 4-bit only to represent numbers? How do we know that? Well, do you remember 2's complement is really the same thing as arithmetic negation, right? So if I know that 1, 0, 0, 1 is representing a negative quantity and I apply 2's complement to it, then I know the magnitude of that negative number. Does that make sense to you? Okay. So we'll go ahead and I'm just going to do this on the whiteboard. 2's complement of 1, 0, 0, 1 is the 1's complement of the same bit pattern plus 1. Okay, that's the definition of 2's complement. The 1's complement of a number is really just flipping the zeros into 1s and 1s into zeros. So it becomes 0, 1, 1, 0 plus 1. And you can see that this is just 0, 1, 1, 1. 0, 1, 1, 1 in binary is 7. So which number's negation is 7? -7. Okay? Whatever is representing -7, if you take the negation of that number, it should give you 7. So that's why we know 1, 0, 0, 1 is actually representing -7 when we use the signed interpretation. Okay, so that's good. The next one, well, if I know this, the next one is pretty easy because I'm involving the same kind of values, right? But the ordering is not the same anymore because in this case, 1 is greater than -7. Okay, I kind of get that. All right, now let's take a look at the last 2 examples here. The last 2 examples, I don't have to deal with anything else because 0, 0, 1, 0 is representing 2 whether it is signed or unsigned. Right? Because it is in the overlapped portion of the number wheel. Okay, it is the same. And so that's why it works for both cases here. So in this case, is there a particular flag that I can use to indicate the ordering of signed numbers or a bit pattern using the signed interpretation? Well, let's take a look here. Let's find out. Let's see if we can find a pattern. Okay, greater than, greater than. The zero flag is useless for this kind of thing because when the zero flag is zero, it simply means they are not the same. Doesn't tell you the ordering. In this case, there's a sign flag being 1 here, the sign flag being 0 here. That means we cannot use the sign flag by itself, right? Well, let's take a look here. The carry flag, nope, cannot use it by itself. The overflow flag cannot use it by itself. Well, yeah, we need a combination, but it's not the combination of the carry flag and the overflow flag. Let's see if we can find out which combination works, okay? Let's take a look at less than here. Okay, this is less than, this is also less than. Okay, when you compare the two cases where we have less than, hey, seems like the sign flag can be used, but we know the sign flag by itself is not useful because it doesn't work for greater than. Or at least the example that we have used already, greater than does not work. Okay, can it be the carry flag? No, cannot be the carry flag. Can it be the overflow flag? Well, maybe it can be the overflow flag, but we already tossed out the overflow flag because it does not work for greater than. So it seems like we are stuck here. It seems like no one single flag can be used to indicate the ordering of two numbers when they are interpreted in a signed way. As it turns out, you need a combination. The combination is the sign flag and the overflow flag. Okay. So what we'll do now is we're going to extend this table a little bit, and then we'll say, what about if I do a overflow exclusive OR sign here? Does everybody understand what is exclusive OR? The four combinations of exclusive OR are what? 0 exclusive OR 0 is 0. 1 exclusive OR 1. One exclusive OR 0 is 1. 0 exclusive OR 1 is 1. And then 1 exclusive OR 1 is 0. Exactly. So exclusive OR simply means one and only one side of the exclusive OR operator can be a 1 in order for the entire expression to be true. Is that okay? I can just spell it out. It's easier just to spell it out too. Okay, so we have exclusive OR. We have two independent Boolean variable A and B, and then we have A exclusive OR B. A can be 0, can be 1. When A is 0 or false, B can be 0 or a 1. When A is true or 1, B can be 0 or 1. And the definition of exclusive OR is saying this is 0, this is 1, this is 1, and this is 0. Okay. Are we doing okay so far with this? What is the bitwise exclusive OR operator in C? Quick quiz in topics of cisp 360. What is the bitwise exclusive OR operator in C or C++?
One line.
The bar?
Mm-hmm.
The vertical bar is bitwise OR, but not exclusive OR. Okay, bitwise exclusive OR is the caret symbol. Okay, the caret symbol means exclusive OR, bitwise exclusive OR in C. There's no logical operator for that. There's only the bitwise operator for it. Okay, so if I know this operator, what would be the result of this part here? Overflow exclusive OR sign in this case will give me a result of what? 1. Sign is 1, overflow is 0, so this will give me a 1. Okay, so we're going to do it for all the combinations here. So we have overflow exclusive OR sign, and this one will give me what? This one will give me a 0, right? Because we have 1 here, we have 1 here. 1 exclusive OR 1 is 0. All right, so let's find out about this one. Okay. overflow exclusive OR sign is, in this case, we have 0 exclusive of 0, so the end result is 0. And then the last one is over here. We have overflow exclusive OR sign, and that will give me a 1 in this case because we have sign being 1 and the overflow flag being a 0. Okay, so do we have a winner now? Come on, let's take a look. Greater than, greater than. Do we have a particular flag that stays consistent in both cases? Yep, we do. Okay, now let's look at the less than cases. We have less than or less than here. Do we have a consistent flag in those two cases also? Yep. It is our new friend. Our new friend is overflow exclusive OR with sign. So when you want to look at the ordering of signed numbers, not a single flag can give you the actual ordering. You have to look at two flags in order to do the same. You have to look at both the overflow flag and the sign flag in order to determine the order of two signed numbers. Are we still doing okay so far here? Go ahead.
So if it turns out to be a 0, then that means the first number is less than the second number.
Well, if you look at this, if overflow exclusive OR sign is a 1, it means the first number is less than the second number. Basically, it's what you said. I think it's just the other way. Yep, go ahead.
So in the less than, we'll always have sign being like 1. Oh no. And overflow sign 0.
Say good.
So less than would have a sign flag of 1 and a variant of 0. Or could that flip flop and be sign 0 period?
The carry is not important.
I'm sorry, the overflow. Sign,
Yeah.
sign 1 overflow.
If the first number is less than the second number when you do a subtraction, then you are guaranteed that one of the two has to be a 1. One and only one of the two flags, overflow or sign, has to be a 1.
Okay.
That's basically what it is.
We didn't have an example of the overflow being a 1 and sign being 0. That's why I wasn't sure.
Well, let's generate a case like that. No, that's a good question. Okay, the question is, can we have a case where the overflow flag is a 1 and the sign flag being a 0?
Yeah.
Okay, so let's do that. So we'll go ahead and the sign flag being a 0, I think. Is that right? Is that right?
Yeah.
Sign flag being a 0, the overflow flag being a 1, and the carry flag, I don't really care. Okay, it can be anything. In fact, from the discussion of last week, we already know in the subtraction, if I say the sign flag is a 0, the overflow flag is a 1, that really tells you the carry flag has to be a particular value. What value is that? What? 1? I think it's the other way around. Well, let's find out. Okay. We can work all this out, using logic here, which is why I like this class. Okay, so let's go back and remember the definition of the overflow flag in the context of subtraction. Okay, so in the context of subtraction, we have A followed by whatever number of bits here, minus B followed by whatever number of bits here, and then the result is our, let's say this is C with whatever number of bits here. The overflow flag in the case of subtraction is basically there are two cases here, and they are joined by an OR. The first one is we have the first number is negative. If that first number is negative and the second number is positive, right? Then we should always end up with a negative number. But if for whatever reason we end up with a non-negative number as a result, then the sign does not make sense. Is that right? So let me double check. The first number is negative. We subtract a non-negative number from the negative number. The result should be negative. But not C means the result is non-negative. So we have a problem. Okay, we have we have a negative number minus a non-negative number. For all practical purposes, let's just call it positive, okay? So the result should be negative. Does that make any sense? Okay, so if the result here is non-negative, then we have a problem. The sign does not make any sense. Negative number means the sign is a 1. Non-negative number means the sign is a 0. Negative number means the sign is a 1. But I want to look for the exception case. So the exception case is we have a plus here, then we have a 0 here. And that's why we have A and not B and not C. The other case is basically the flip case of this, which means we start with a non-negative number, we subtract a negative number from it, and we end up with a negative number as the result. Okay? Okay, so now knowing that the overflow flag is defined like this, and in our case, we want the sign flag to be a 0, right? So we want the sign flag to be a 0. If the sign flag is 0, we can actually plug it in because the sign flag is actually our C here. So that means, you know, we only have a chance, you know, on this side. Okay, let me just use the overlay way of looking at this. If the sign flag is a 1, that means, you know, this is a 1 here. So that means this side is the only side that has a chance to become a true statement, because this not C is going to be a false, and since this is a big conjunction, any part being a false means the entire thing is false. So in order to make this part true, I need the B to be also a 1 and the A being a 0. So that really kind of sets the stage of, you know, what kind of case am I looking at in order to create that particular pattern. Now, because, you know, we are subtracting a 1 from a 0, that means, you know, the carry flag is also guaranteed to be a 1. So I just solved the first problem, which is, you know, okay, can we determine the value of the carry flag just knowing the sign flag is a 0 and the overflow flag being a 1? And the answer is yes. We can, you know, determine the carry flag just like that. So the next question is,
Wait,
how?
Is the sign flag 0 or 1? Because at the bottom of the sign flag is 1.
Huh?
At the bottom of the sign is the 1, but at the top you say sign 0, which one's in?
At the bottom, we have the sign being.
You see the overflow equals that?
Right. Okay, I flipped. I was working on the wrong case. Okay, because, you know, we want to work on this one. I saw the other one. Okay, forget about this. Okay, so we want this to be a 0. So for this to be a 0, this has to be a 0, and this has to be a 1. So we have a 1 minus a 0, which means the carry flag has to be a 0 in this case. Okay, sorry about that. All right, so now we have, you know, a pretty good indicator already, because the subtraction in binary has to go like this. We are looking at something that looks like this: 0 blah 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 minus 1 blah blah blah, ending up with. Oh, I flipped it again?
Yeah.
Yep, I did. 1 0. And this has to be a 0, blah, blah, blah. Okay, so we're looking for something that will give me this kind of result. All right. So we are, well, that's pretty easy. That's easy to do.
1 0 0 0 1 1.
That would do it. Okay. Okay, so that case, you know, will generate the flag combination that you asked for.
But how will that have an overflow being 1?
How would that have an overflow being a 1? I am subtracting 1 from negative 8 and I'm getting 7. Yep. The less than? Oh, okay. Let's take a look. This is negative 8, and that is a 1.
Right, okay.
So we have negative 8 being less than 1. Whenever the first number is less than the second number in sign interpretations, the exclusive OR of overflow and sign will be a 1. So that is consistent with that observation.
So when the first number is the left joint section number, using our XOR,
the exclusive OR of the overflow flag and the sign flag should be a 1. Absolutely. We have a less than here, and then the exclusive OR result is a 1.
So,
This one doesn't.
Anytime your most significant digit is a 1, you treat it as the negative version.
I'm thinking like symbolic logic right now.
No, because we're trying to use the sign interpretation because we are okay. The context of this is we are representing signed numbers using formulas. Is that okay? And in order to compare these numbers and figure out which one is larger, which one is smaller, we use subtraction as a mechanism to set the flags. And then we want to interpret the flags in order to find out, okay, so exactly tell me which number is larger, which number is smaller. Or to be more exact, you can tell whether the first number is smaller than the second number or not.
So you're comparing negative 7 to 1001. And you're saying that's less than 1 makes sense.
Yeah.
But how come 1 is staying 1?
They have inclusive OR.
And
Because 1 only has one representation.
Either one.
All the non-negative numbers have the same representation, whether it is a signed interpretation or unsigned interpretation.
okay, so then would there ever be a time you'd want to compare the positive representation of 1001 against
Yes.
the second
You can
number?
have
Absolutely.
them to be true.
And how then you would know that based on which flag is set?
So yeah.
When you are comparing unsigned numbers, then we have already determined which flag is going to be the result. It is the borrow flag. So for unsigned comparison, you pay attention to only the borrow flag. For signed interpretation, you have to pay attention to 2 flags because the exclusive OR result of the overflow and the sign flag will tell you the ordering of 2 signed numbers. Okay. You can actually set up examples. Okay, so before we leave today, I will leave you one thing, which is not a assignment that I'm going to grade, but I'm going to give you a tip of how to work on this kind of thing, and how to run some experiments on your own, so that you can experiment with these things and say, oh, okay, I get it. Okay, so we'll do a compare program here. So in this compare program, we'll just go to the text section here, dot global underscore start, and the way you do it is pretty simple. You just have to move a particular constant into, let's say -5 into EAX, and then you can do a compare instruction, CMPL. And when you do a compare instruction like this, I'm going to tell you exactly what it is going to do. Okay. So this is the same as subtracting. This will subtract -7 from EAX, but the result is not stored. Okay, so just by running, just a whole bunch of little programs, but putting different values into the 2 immediate operands, then you can actually see how the flags are set in the end. If you don't want to deal with 32-bit numbers, you'll just change the L to a B and then change EAX to AL, because that way it's easier to look at the bit representation as an 8-bit instead of a 32-bit thing. But I would strongly recommend you guys to kind of do this kind of exercise and just kind of figure out, okay, this number, 255, is also -1. Okay? So when you do the comparison, does it matter how you represent that number? Yep, go ahead.
For 0, we have jump 0, JZ, yeah?
Yep.
JNZ.
Yep.
And for these flags, which?
It's the same as the names. So you have JO, JS, JC, JNC, JNO, and then JNS. Okay. But there's one that is a handy feature. You have JL and JNL as well. Go ahead and read the conditional branch section. You will see all the possible combinations. But for the time being, I'm going to use this one here. So the question now is, does it matter whether I specify this number as -1, 255, or in hexadecimal FF? The answer is no, it does not make any difference whatsoever. Because -1 as an 8-bit number is has the same bit representation as 255 as an 8-bit number, which also has the same bit representation as 0xFF as a base 16 number. So all of those specifications will give you exactly the same bit pattern in AL. And since they're the same bit pattern, the compare instruction will end up with the same result. Okay? So this is a kind of opportunity for you guys to play with the compare instruction and just kind of figure out, okay, what flag combination will be the result of this compare. I would suggest you to come up with some cases and figure out by hand what would be the combination of flags, and then run the program like this in GDB, and then figure out, okay, is that really the case, and validate your own answer that way. Okay. And you probably want to figure out all the possible combinations too, and say, can I figure out an example to make that happen? That's basically what the homework assignments used to be doing. I don't assign that anymore because if you watch the video from last year and the year before last, you can get the solution right away. So I'm not gonna I'm not gonna assign that assignment because there's no point in assigning something where people can just watch past recordings of this class and know the answer.
What happened?
Hmm?
What happened?
To make a particular flag combination happen. Well, there are some that are impossible. We talked about that already. So not counting the impossible flag combinations, find a way to make this program changing just the immediate operand to make all of those possible flag combinations happen. That would be a worthwhile exercise. Yep. You say I are.
Oh, good. It's so big as nobody really wants to do. I can see like 10 people. Maybe now. What's going on? Talking about philosophy. You're taking like a philosophy class?
I took an intro to philosophy class once.
You like it?
One question, professor.